Right, we're carrying on with this metal acid worksheet. So what you've got is, let me use the mouse. You've got an acid and you've got a metal. So what did we say about that? We're expecting mush. This is what we're going to remember out of it. So that's a metal. This is an acid. If you react them together, you get salt and you get hydrogen. Now from there, what did we say you're going to observe? You're going to see effervescence, which is another word for bubbles. And you will see the metal getting smaller. Metal gets smaller, or you can say metal disappears. Right, and they've got a thermometer here, and that's to measure the temperature. Right, so be careful with these because they're not as easy as they look. Sometimes they go to half a degree, so be very careful. It's very deceptive. So look, you've got 25 here, 26, 27, 28, 29, 30. I just wanted to make sure. Right, so I know that's going to be 26, 27. So it's 27 degrees before, right? And it's gone to 30 there. Can you see that long line? That's 30. That's 31. That's 32. That is 33. So this is 32.5. So 30 after adding zinc is 32.5, and then you just subtract these two. Yeah. Okay, let's do that. That will be 5.5 degrees. Right. Student wants to find out if there is a relationship between the reactivity of a metal and the temperature rise. He repeats the experiment 4 times using different metals. Right, 3 factors that the student should keep constant. So we're looking at temperature rise for different metals. What should he keep? Ah, okay. So keep the concentration of acid the same, the volume of acid the same, and the you can say the mass and the what's the word, what state it's in terms of a powder or surface area. That's the word I was looking for. Keep the surface area the same. So you'd use I don't know, 2 grams, 2 grams, 2 grams, 2 grams, and then you can use them in either block form or powder form. Just keep it consistent. Either ribbon, flat, whatever it is, yeah. Okay. Right, okay, I was just looking up something. Because I was a bit confused as to what's going on. That's fair enough. No problem. No problem. No problem. Concentration, surface area, moles. Okay, right. Using information from the table, state the relation between reactivity of the metal and temperature rise. Okay, sorry, I'm a bit zoned out. Right. So we know, let's go up. We know the reactivity series. What is it? Please stop losing careless marks always. And then we put chicken, CH, carbon, hydrogen. These are non-metals. They're just reference points. And then you've got zinc and iron. Zu is, and then you've got copper, silver, gold. Right, that's potassium, that is sodium, that is lithium, that is calcium, that is magnesium, this is aluminium, zinc and iron. Magnesium is here. Gold doesn't react by the looks of it, so it's there. Iron is there, and calcium is here. So we're expecting calcium to be the most reactive. So this is the most reactive. This is the least reactive in this list. So because you've got the highest temperature, that's the most reactive. That's the least reactive. That's the second most reactive. That's the third most reactive. And you can see it should match up. So you should have green at the top, red, blue, purple. So what can we say? We can say the more reactive, sorry about the capital letter, the more reactive the metal, the more reactive the, did I just write that? I believe I did that. Oh, the higher or the greater the temperature rise. So why there is no important rise when gold is added to acid? Because there is no reaction. There is no reaction taking place. Okay, there you go. Let's move on. Question 14. How are we going to plot this? Right. So they've given us the labels, the axes labels, and we need to just plot it. So it's going to be a curve, so it's going to be 1 and then 14, so that's 10, 12, 14, 16, 18, 20, so it's going up in twos, so we want to be there. So after 2 minutes it's 37, so 32, 34, 36, and halfway between 37. Right, 928, 340, 340. So let me just do it with a different color. So you're gonna, oh, I can't believe that. This is the world's greatest curve. Right, let's carry on. 449, 449, 5, 54, 6, 58, 7, 60. That means the reaction is complete. So right, okay. So watch this. Now, have you noticed? Ooh. Right, I'm going to spoil it a bit now. Right, if I did a proper curve, it'd go that way, and it'd try to follow that line. Can you see that line there? There you go. But there's something gone wrong here. So that is the anomalous result there. That one there. Because it's not quite following the trend. So in 2 minutes, we've collected more gas than we were expecting. So we were expecting around 28 in this region. But that's when you plot that, right? Okay, I just wanted to show that because it's easy to mess up. How many marks? Oh, it doesn't matter. I can't see it. Right, okay, so now we're going to that. We're answering that question. The result at 2 minutes is anomalous. It means away from the normal. It does not follow the trend. Does not follow the pattern. Okay, as we expect it to. This saying suggests a mistake that the student could have made. Right, the student could have measured the volume of the gas after 2 minutes. Yeah, or he could have misread the syringe. He could have misread the reading under, misread the syringe reading. Okay. Use your graph to estimate the volume of gas that was given after 2 minutes. Right. What they want you to do is go to 2 minutes, draw a line up to your graph, and then draw a line across. So we were expecting 28. We were expecting 28. And look at this. Show clearly how you obtained your answer. So they want them to these two lines. Right. Explain why the last 4 readings are the same. Because the reaction has finished. The reaction has completed. So the reaction is complete. Why is it complete? Because all the acid has reacted or been used up. Let's look here. So look, they've used excess zinc powder up here. Look, there's a clue here. Excess zinc powder. So that means all the acid is going to react. If they'd said excess acid, all the zinc would have reacted. Right, let's move on. State how the graph shows that rate of reaction decreases in the first 7 minutes. The gradient of the curve decreases. Gradient of the curve decreases. Explain in terms of particle collision theory. Right, okay. So what happens? So look at it this way. So there's the acid. There's the zinc. So what happens is this zinc needs to hit collide with this acid. And because there's lots of them, there's more chance of it hitting each other or meeting somebody. It's like being in a busy room. You're more likely to bump into somebody. But if there's only two of you and you walk around, it's unlikely you're going to bump into each other. So what happens is at the beginning, look, he bumps with him, he bumps with him, he bumps there, he bumps there. So now that these guys have gone, right now there's a bigger space. So these after this here, this has to travel further, this has to travel further, this has to travel further, and if that's moving in that direction, that might have to hit that. So what they're saying is there's fewer particles as time goes on, fewer particles of acid and zinc or metal to react. So that's your first point. Second point is, so fewer successful collisions per unit time. Right. So you've right, okay, this is that polystyrene cup. This is the standard one. You've got a cup. Why do we use polystyrene? Because it's a good insulator of heat or poor conductor. You've got your thermometer, which is measuring the temperature. You've got acid and zinc. So you put your acid in. Right, okay, let's just redo that because it might cause a bit of confusion. Right, I've got a beaker here. I've got acid in there. And I'm going to pour in some. If I pour in some metal or zinc, that's what I'm doing. Then I'm going to stir it and measure the temperature. We do it 3 times. Experiment 1, 2, 3. So these are your results here. Now we need to read initial after 1 minute temperature increase. So initial, let's just try to read. Let's say got a half somewhere. Yes, they have here. We look at 3. So look, 10 there, 11, 12, 13, 14, 15. Have you noticed this is slightly longer? That's 15. So we've got 16. Right, so we've got 16 degrees at the start, and then we've got, look, 20, 21, 22, 23, 24, 25, 26, 27, and a half. So we've got 16 and 27.5. And then if we subtract those, we get 11.5. Explain why the temperature increase changes as the concentration increases. Right, as the concentration of acid increases, you've got more particles per, how can you say it, per unit volume. So that means that there's, first of all, the reaction occurs more quickly, or the rate of reaction increases, occurs more quickly. Why? Because of that collision, particle collision theory. But so why does the temperature increase? So the heat energy, so the heat energy is released quicker to the water. Yes, more quickly. So it's only a 2 mark anyway. Right, the student does another experiment at the same initial temperature as 3. She uses the same size but uses 25 centimeter cubed. So they use 50 here. Yeah, okay, so they've used 25. So understand that. So look, the initial one was 50 centimeter cubed. This one is 25 centimeter cubed. The student does another experiment, right? Okay, in excess, both. So explain the effect, if any, on the initial rate of reaction. Right. The rate of reaction is same because you have the same you can say, well, I would have said the same concentration of acid and same surface area. Right. But you can also say that you've got, because the initial temperature is the same, they've not made any changes except they've put 25 centimeter cubed here instead of 50. Right. Explain the effect, if any, of this change on the temperature. So what's going to happen is, because you've got more volume to heat up with the same energy, your temperature increase is going to be lower. That makes sense because there's less to heat. Sorry, there's more to heat. So you use the same amount of energy to heat a smaller volume of liquid, you're going to get a bigger rise. So first of all, what's going to happen? You're going to get a greater increase in temperature because you have the same amount of thermal energy or energy but a smaller, we discussed this earlier, didn't we? Smaller volume of liquid or solution or acid. It's acid initially and then it reacts to become a zinc hydroxide. Right, okay, let's have a look. Is this 16 to, yep, okay, this is the last one. See if we can squeeze this one in. Because these questions are really useful. Just keep going them and you see how easy they are. So we've got magnesium ribbon and dilute HCl. Right, we know magnesium ribbon is a solid. We know hydrochloric acid is aqueous. Magnesium chloride will be aqueous and hydrogen gas will always be a gas. Right, okay. We clean the strip to help the rate of reaction because there's a layer of oxide on the magnesium ribbon. It reacts with oxygen in the air. So 50 centimeter cubed, 0.5 moles per decimeter cubed. That's the concentration. As soon as you put the magnesium ribbon into the flask. This bung goes on here as quickly as you can to stop losing gas, the hydrogen gas that's produced. So record the volume of gas every minute for 8 minutes. So then, okay, and you've got your stopwatch here. Right, so that's why the student cleans. Why would you clean? To speed up the reaction, to make the reaction go faster. Right, remember we said to remove the oxide layer because it slows it down. You can say that as well, to make the reaction go faster. So that's why the student needs to put the bung on the flask quickly. Right, so little gas escapes. Yeah, so just when the student should start the stopwatch, as soon as the bung is placed on the flask. Oh, okay. So these are the results. Have you noticed here, look, let me get the notes. So it goes up at a steep gradient and then it starts becoming less steep, and eventually at this point here, there's no more gas produced. It's hit that magic 60 centimeter cube mark, so that means the reaction is complete. Now, I'm thinking that they put in excess metal. They said that. No, okay. Yeah. They've not said how much, so the reaction stops. Right. Use the graph to find the volume of at 1 minute. So what you do is you get your ruler, draw a straight line up to here, and then you read across. So that should be 22. So we need to use the graph to find out when the reaction stops. So remember we said there was this point, magic point here where there's no more gas produced. They can be a bit strict actually, so I would say 5.2. 5 minutes 12 seconds. Are we allowed to say that? 5 minute 5.2, 5.3. Okay, you can put it in decimals. They've put 5.3. We read it as 5.2, but they give a range between 5.3 to 5.4. In fact, it says 5.2 to 5.4, which is okay. So they've given us quite a bit of leeway, quite a good range. Right, what else is there? Oh, okay, that was it. Right, well done. We'll call it quits at that.